So, welcome to Physics Live once again, and we are discussing the mathematical physics in which I am going to discuss the Fourier transform in this lecture, which is a part of integral transform. Now, what is the importance of the integral transform and what is the process of integral transform? At first, we have to study this, and then I will show the different process of integral transformation. We have only the two main process. The one is Fourier transform or Fourier integral transform, more correctly we can say, and another one is Laplace transform. So out of these two, today we will discuss only the Fourier integral transform. Now at first you have to know what is the importance of the integral transform. So integral transform. Integral transform is a mathematical process in which we can transfer some function from one coordinate system to another one. What I mean to say, one physical coordinate system to another physical coordinate system. Now you have studied the quantum mechanics and you know very well about the importance of phase space. Rather, you have already studied it in the statistical mechanics or in classical physics or classical mechanics. That the importance of phase space is very much crucial. Why? As because it is sufficient to describe the motion of a particle or the system of particle. Okay. So the phase space consists of the position coordinate system and momentum coordinate system. Suppose I have denoted these as x and p, and you are given a quantity or function in the position coordinate and you have to transform it in the momentum coordinate. Then how can you transform it? With the help of the integral transform you can easily transform it. This is one of the important aspect. Okay, so integral transform, there are many process of integral transform, but we here concentrated on the two of them. One is the Fourier transform, and another one is Laplace transform. Out of these two, Laplace transform is very much easy as compared to the Fourier transform, but the physical significance of the Fourier transform is very much uh, high. Okay, that is why we are going to discuss the Fourier transform at first. So now I was telling that the integral transform helps us to transfer some function from one coordinate system, obviously the physical coordinate system, to another physical coordinate system, and it helps, or it also contains some many applications in first quantum mechanics. Huge application is there in the quantum mechanics you will study in the upcoming semester. It is highly applicable in the solid state physics or condensed matter physics. Why? Because you have already known to the fact that uh, okay, let me write first condensed matter physics. Okay, so you are known to the fact that the solid are composed of some unit cells. Solid state crystallographic structure consists of some unit cells which are also based on the crystal lattice. Okay, now what is lattice? Some bases and uh, the lattice point. Okay, lattice plus basis forms a crystal. You are known to the fact. Now suppose uh, you are given a wave vector in the x coordinate system, and you have to that is a position coordinate system, and you have to transform it in the momentum coordinate system. Then how can you transform it? With the help of some solid state process, solid state techniques, you can transform it. And the crucial concept here is the reciprocal lattice, which was uh, postulated by Ewald. Okay, So the reciprocal lattice concept is very much important in the study of crystallography in the solid state physics or condensed matter physics. And in the crystallography, you have to apply the Fourier transform to uh, make the transition from the position space to the momentum space, that is from direct lattice to reciprocal lattice. You have to apply some transformation. Okay, so in the condensed matter physics it is also highly applicable, as well as it is applicable in the electronics. In the digital signal processing, you have to apply the Fourier transform. Okay, so you can write it here that in electronics it is also applicable. In which branch? Digital signal processing. Some of you may have this on your dissertation. Okay, digital signal processing. It is very much interesting topic, but this is not the matter to discuss in this video. So let us begin the Fourier transform. Okay, so um, you have to first know the basic process of integral transformation. In this case, you have to transform some function from one coordinate system to another. Okay, and you can denote it as I of fx. What does it signify? It signifies that the integral transformation of the function fx. How can you write this? Like this way. Some limit is there, and the function, and this is the interesting thing. Sorry. K of Sx dx. Okay, what is this? If you integrate fx dx, simply it will give some area. Okay, not any function at all. But when you multiply this term, it will give you your desired result. It is known as the Please hold on. Okay. So I was discussing that these new function have to be multiplied in this integration. Why? It is known as the kernel, because this function will lead to you uh, to result the fx into the another function, which must be some function of s, and because of this is Fourier transform. Okay, so it is the general transform I have written. So you can put any name, but I here put the capital F. Okay. So what is the role of this function, which is known as a kernel? To transform this fx into some another function, which now transferred to another variable s, because it is both the function of s and x, and the x variable term will goes over on the integration, and the s variable term will only present, so that we will be able to transform this fx into the another variable function. This is known as the transform function, which is obtained by the integral transform. Now, depending upon this kernel, we can classify the Fourier transform and Laplace transform. In the Fourier transform, in the Fourier transform, the kernel is written as the total formula I want to write. Fourier transform of fx, it means this is nothing but this, this, and this. Many questions will be coming on your mind, that why it is necessary to multiply this factor, and this is applicable to some limit minus infinity to plus infinity. This is nothing but due to the normalization constant. You will learn in your quantum mechanics also. This is nothing but the normalization factor. Okay, it is a constant. Uh, it will not change the function, but it will help you to normalize the function. what you have chosen. Okay, so here you can notice that the kernel is nothing but the e to the power isx, whereas if I want to write the Laplace transform, the Laplace transform, same, sorry for the disturbance. So in case of Laplace transform, the kernel chain Laplace transform of some function fx, which you can write Laplace as a function is, and you can write this to be 0 to infinity fx e to the power minus sx dx. Okay, so here you can notice that the kernel here is e to the power minus sx, whereas the kernel in case of Fourier transform is this. So depending upon this value of kernel, we can classify them as the Fourier transform and Laplace transform. Now, one of the important application of these two integral transforms is nothing but to solve the ordinary differential equation, ordinary and partial. Okay, to solve the differential equation you can write, solve the differential equation. This is another more important application of these integral transforms. Now let us move on. So we will discuss in detail about the Fourier transform. So what I have written here is nothing but the Fourier transformation of fx is 1 by root 2 pi integration minus infinity to plus infinity fx e to the power isx dx. It will be written in 1,000 times or 100 times. Okay, so it will get automatically memorized to you. But the important fact here is that many books consider this to be equal to 1. I will say this why this variation occurred. At first you have to understand the if you have the function in the s coordinate system and you have to revert this function to the x coordinate system, then how can you do this? In this case you have to apply the inverse Fourier transformation, that is Fourier transformation of fsx, which is nothing but the inverse Fourier transform small fx, which is also equal to 1 by root 2 pi minus infinity to infinity f s e to the power minus isx ds. See, here the variable changes to ds. Okay, so here the variable changes to ds because the function is inverse Fourier transform and you will get the function in x coordinate system, and in this case the kernel transferred into the e to the power minus isx. Okay, now many books choose 1 by root 2 in this 1 by root 2 pi to be 1 by 2 pi and this to be the 1. Okay, why this difference arises, or why the authors have the flexibility to choose this? It is answered when you know the integral theorems. There are some integral theorems which you must have to know to understand this fact, but because of the shortage of time, this thing will be discussed in another video. But you have to understand these two formulas very well. One of the formula contains the Fourier transform of fx and the another one is inverse Fourier transform of fs. Okay, so now that the Fourier transform of a function can be written as f of x is nothing but 1 by square root 2 pi minus infinity to infinity fx e to the power isx dx. Okay, now I can show you one beautiful interesting function. You have to suppose find the Fourier transform of ax square e to the power ax square. Suppose this is your given function, you have to find out the Fourier transformation of this function. If you plot it, let us try to plot it. Okay, let us try to plot it. um, e to the power minus ax square means it will be a Gaussian curve like this. Okay, and this is some half power frequency, or this projection gives the bandwidth of the Gaussian function, which is known as the full width half maxima. These are the half maxima points, and this range gives the full width half maxima. Okay, so you have to find out the Fourier transformation of this. So put it in our definition. So f of s will be nothing but 1 by root 2 pi integration minus infinity plus infinity e to the power minus x square e to the power I is x dx. How can you get the result? Some tricks you have to apply here. At first you have to minus x square, you have to transform this. What does is result? E to the power minus x square plus isx. Now you can make it by taking a as common as a quadratic equation. How? Minus I is x by a, okay, plus I square is square divided by 2a whole square. This term is new, so it must have to be subtracted. So I have written it as like this: I square is square divided by 4 is square. Okay, so the exponent part result out to this. Now you can easily say that this forms a quadratic equation, and you can simply write a x minus I is divided by 2a whole square. This and this another term you can separate out like this: 4a square, this plus minus minus plus dx. Now this is constant term, you can get it out from the integration, and I square means minus 1, so this is becomes this, and this becomes minus infinity plus infinity e to the power minus a x minus I is divided by 2a whole square dx. Now to simplify this, I can choose x minus I is by 2a is z, so dx will be nothing but dz, and the limits will be same, so I can transform the total integral as this: squared by 4 is square infinity 2 plus infinity to the power minus az square dz. Now it is very much simpler: 1 by root 2 pi and root pi by a square by 4 square. The result of this is root pi by a. By uh, studying the complex analysis, you can obtain this, but you have to memorize this formula. So what did you obtain here? 1 by root 2a e to the power minus a square divided by 4 square. I had done my job. This was given the function of x, and it is transformed to the function of s, provided the nature of the functions is same. It is carefully, it should be carefully noticed that the nature of two functions, that is by transferring the coordinates as well, the nature of this function remains same. This is the only function which is known as the Gaussian function. So you can write that Gaussian function is self-reciprocal. Why? As because in the reciprocal space it also contains its identity, so it can be said that self-reciprocal. Like simple cubic crystals are self-reciprocal. You can be Uh, Proof in the condensed matter physics that the simple cubic structure in the crystallography are also self-reciprocal. That is the reciprocal space, the simple cubic structure remains the same in nature. Okay. Okay. Now, the main purpose of our discussion. Okay. Before discussing this, let us discuss the Perseval's identity regarding the Fourier transform. Okay. Next thing is the Perseval's identity. Perseval's identity in Fourier transform. It is something different like the Fourier, like from Fourier series. Okay. So let us write. At first, you have to consider something like suppose the Fourier transform of fx is fs, Fourier transform of another function gx is gs, and the complex conjugate of fx be fx bar, which is nothing but complex conjugate of fx. Likewise, gx bar is the complex conjugate of gx, and similar for those this and this. These are nothing but the complex conjugates of fs and gs respectively. You have to consider these as first. Okay. Now, what does the Perseval identity say? It says two things. First, minus infinity to infinity when you proceed with fs, that is the Fourier transformation of fx, and multiply the complex conjugate of gx. What does it mean? The complex conjugate of the Fourier transform of gx. When you integrate it over ds, it will result out minus infinity to infinity fx complex conjugate of gx dx. Okay, simple, but you have to prove it. I will show you the proof. But the second thing is that it is very much helpful or very much applicable from the first one, that fs square ds is minus infinity to infinity fx square dx. Okay, both things will be you can find out. So let us see the proofs. So at first it is given to you minus infinity to plus infinity fs gs bar ds. What does it mean? It means minus infinity to plus infinity. You can explain this. How? Fs can be written as fx e to the power isx, okay, and 1 by root 2 pi 1 by root 2 pi fx e to the power isx ds. Sorry, dx. Dx. Okay, this part is covered up. Now gs bar is present here as well as ds is present here. Now you can arrange them in a proper way, fx, and we can arrange it in such a way that this gives out this, uh, this, this, this. Okay. So this case, if I have written this. Okay, I think it will be something difficult for you. No, no, not the difficult one. You can arrive it. So, what does it signify? Minus infinity to infinity. This is nothing but the uh, inverse Fourier transform of GS bar. Why? As because GS e to the power ISX ds 1 by root 2 pi minus infinity to infinity. This gives out some gx. Okay, but when you find out the complex conjugate of total equation, then the complex conjugate of gx will be complex conjugate of gs will be complex conjugate of e to the power minus isx. So it will result nothing but the gx part and the dx. So the first part is proved. Now it is the time to discuss the next part. This is not something new. If you consider both gx, the gx is also the fx, then you can easily obtain these at mod fx square dx, and this is also nothing but the complex conjugate of fx will be fs bar. So you will be able to obtain this. Okay, once you prove this, it is not very difficult to prove this. What I am doing, gx is also fx. I have considered this is the special case of the first one. Okay, the gx is equal to fx, so gx bar is fx bar, and the Fourier transform of fx is fs, and the complex conjugate of fs is fs bar. So by multiplying fs with fs bar, multiplying fx with fx bar, you will result this and this. So it is very easy to prove, nothing difficult. First one is something tricky, but the second one is the special case of the first one. Now I want to show you some of the properties of the Fourier transform to solve our purpose. Okay, so the first property of Fourier transform, not all the properties are necessary to know for us. I want to solve the differential equation with the help of this Fourier transform, so that I have to find out some of the properties which will be helpful in solving this. So we have learned that the Fourier transform of fx is 1 by root 2 pi minus infinity to infinity fx e to the power isx dx. Okay, so by using this definition you can find out the differentiation of Fourier transform. Okay, how? Let us find out the Fourier transform of the derivative of fx. So by our definition we can write this fx bar e to the power isx dx. Now you can integrate it by parts. So 1 by root 2 pi, and this is e to the power first function integration of the second, first function integration of the second, this minus infinity to plus infinity, and minus derivative of first function integration of the second. derivative of first function, integration of the second, this dx minus infinity plus infinity. Now, when you are asked to find out the Fourier transform of the derivative of a function, it is given to you if and only if fx tends to 0 as x tends to plus minus infinity, then you can do this. F of f prime x, in this case this term will goes over to 0, as because e to the power um, at x is equal infinite fx will be 0, and at x equal to minus infinite e to the power will be 0. So the total term will get cancelled over and we can only get minus is. This is what? Fourier transform of fx. So Fourier transform of fx. Okay, nothing more difficult. Likewise, you can be able to find out the double derivative, triple derivative, and so on. I want to generalize it, so that I have considered the innate derivative. Innate derivative of fx, because it will help me to solve the differential equation. So the innate derivative can be written as the Fourier transform of the innate derivative of x from this minus is whole to the power n, means minus is whole to the power 1, f of fx means fs. Okay, now by applying this definition some properties are generated which you can prove also. F of del 2u del x2 is minus of a square f of ux minus of a square u bar, where u bar is Fourier transform of u with respect to x. Okay, so it is nothing but the second order derivative of u with respect to x, uh, and this is from the definition you can easily see. Minus I is whole to the power 2 minus minus plus I square means minus, so minus s squared f of this. Okay, and this I have written as u bar for simplicity. Likewise, you can also able to obtain the Fourier cosine transform of f prime x. It will be helpful for us. SFS is minus root 2 by pi f0, provided for x tends to infinity fx tends to 0. This is the condition. It will also be given to your question of differential equation. Third one is based on the Fourier cosine of double derivative of fx. It is minus a square f of c Fourier cosine of this minus root over 2 by pi f prime 0. Okay, this is also contains the same condition. This was based on the Fourier cosine transform. Now the same thing can be able to obtain Fourier sine. Fourier sine of single order derivative of fx can be written as s f c s with a negative provided the same condition, and the last one is Fourier sine of f double prime x is nothing but minus a square Fourier sine s plus root over 2 by pi f 0 multiplied by some is. Okay, this also contains the same condition. Now we have to prove it, otherwise it will be like the thing which you have to memorize. So let us see the proofs. First one is easy. I'm not going to show the first proof. The second one you have to prove, and the if I am going to show you the second one, then you can also obtain the fourth one. If I am going to show you the third one, you can be able to obtain fifth one. Okay, so one sine and one cosine I want to show you. So at first this I want to show you how this result arises. Now Fourier cosine of this, from definition you can write root over 2 by pi 0 to infinity f prime x, sorry, cosine I have chosen, so cos of sx dx. Okay, from the definition you can easily transform this Fourier transform into the Fourier cosine transform. This, now you have to integrate this by the integration by parts. So root 2 by pi first function integration of the second minus derivative of first function integration of the second, so cos of sx with some s 0 to infinity fx dx. Now multiplying this with this, you can be able to obtain s. So I have the derivative of cos x is sin x, so sin x. So s of root 2 by pi 0 to infinity fx sin sx dx. It will result nothing but the s into Fourier sine transform of fx. Now if you put infinity in the position of fx, then you can be able to obtain 0 for this condition. If you put the 0, then this will be f0, so f0 multiply by some 2 by pi, and this is the plus, and this is lower limit, so this should be negative. Okay, so if I am going to write it in the fresh way, then it gets result out that s into fs of fx minus of root 2 by pi f0. Like the similar way you can be able to prove this one, and like the similar way by the successive integration by parts you can also be able to obtain the 3 and 5. Just I am want to show the 5, as because I have choose sign some sign I want to show you. Simply put it into the definition, root 2 by pi 0 to infinity f double prime x sine of sx dx. It is nothing to get worried. Where you have given sign, put here sign. So this also I apply the integration by parts. So this now first function integration of the second, integration of the second, minus derivative of first function, integration of the second. Okay, so now here the condition slightly changes. As x tends to plus minus infinity, a prime x tends to 0, so that it will get cancelled out. Why? By putting infinity this term 0, by putting 0 this term 0. So the first term has no contribution, so only the second term is present. Root 2 by pi 0 to infinity f prime x cos s x dx. What does it mean? Fourier cosine Fourier transform of f prime x. So you can easily write minus of s f c f prime x. Okay. Now cosine of f prime x I have already written. Put it here, put it here, so that you will be able to obtain minus of s is f is this minus root 2 by pi f0, so that you can get minus of s squared fs s plus root 2 by pi is f0. So this is also proved. Okay. So now the rest of you, the rest of the formula you can derive on your own. One thing I also want to mention, that while you are finding the second order, the condition is if prime x tends to 0 as x tends to infinity. While you are find the first order derivative, if x tends to 0 at x tends to infinity. Okay, and here lies the difference. Okay, let us move on. Why this formula I have written? Let us show you one of the example how to solve the differential equation with the help of Fourier transform. So the question you are given, suppose solve k del 2u del x2 is del 2u del t2. Sorry, I want to solve first the heat equation. So heat equation contains the single order derivative of time with respect to time, and double or second order derivative of u with respect to x. And the condition you are given, u at 0 t is 0 and u at x0 e to the power minus x. All the condition you should have to apply is bounded. Now I have mentioned all the formula in sine and cosine terms. You can see here all the formulas mentioned here is based on the sine and cosine term. Cosine, cosine, sine, sine. When you have to apply sine, when you have to apply cosine, this should be come to your knowledge. Here see, the initial condition at x equal to 0 is 0, which is resembles very much with the sine card. Sine 0 is 0. So you have to apply the Fourier sine series here. You have to identify which kind of transformation you have to apply by see the boundary condition. Okay, so taking the Fourier sine transformation on both the side, we can get root 2 by pi 0 to infinity del 2 u. Sorry, at first I want to write the left hand side. U is capital, so del 2 u del t, sorry why I am del u del t sine of sx dx is equal root 2 by pi k 0 to infinity del 2 u del x2 sine of sx dx. Nothing more critical or difficult. Now you can take out of this del t operator outside the integral, because these are independent to each other, and you have to put this root over 2 pi inside this integration, or outside you can keep, but you should keep in mind that these results to something. Which kind of this? Let us suppose this is u bar. What is u bar? U bar is the Fourier sine transformation of u. Root over 2 by pi 0 to infinity u sine sx dx. For simplicity I have write this. So this is equal to, now in this case you also apply, this is not independent function because this is also ddx, this is also dx, so these are not independent. In case of del t you can easily put out inside the outside the integral, but you cannot do the same thing for this case. What you have to do, you have to apply the formulas that I have already mentioned. So Fourier sine transformation of double derivative, this formula, fifth one, what does it signify? Minus s square fs, this. So minus k is present by default, so I can write k minus s square fs of s. So fs of u, okay, fs of u, and plus root over 2 by pi s f0. Now it is given to you that ux0 is e to the power minus x. So is it capital or small? I think it is small. Okay, you can also take the capital one, no matter. So del u del x signifies del u del x signifies minus of e to the power minus x. So at x tends to infinity, u prime 0, or u prime tends to 0, more correctly we can say. So this is applicable to the condition this condition is also satisfied, so we can easily apply this formula plus a save 0, and a save 0 means at x equal to 0 the functional value of a, at x equal to 0 the functional value is 0, so here nothing but 0. So the term present here minus k a square fs of u you can write as u bar. So u bar, now put it here in the right hand side, so del u bar del t plus k is square u bar 0. It is easily solvable, linear differential equation which is easily solvable to this c1 e to the power minus k square t. Now you have to find out the value of c1 from this condition. At t is equal 0, u bar is c1, again u bar is root 2 by pi 0 to infinity u sine sx dx. This is u at t is equals 0. U at t is equals 0 means this. So root 2 by pi 0 to infinity a to the power minus 6 sine of a6 dx. By doing this integration you can obtain root 2 by pi a to the power minus 6 1 plus a square minus of sine a6 minus s cos a6. This 0 to infinity. Putting the limit you can easily obtain that this function will be goes on to 0, because at infinity this term 0, at 0 this term 0, so only is by 1 plus a square will be left off. This is nothing but the C1. So u bar is from this by applying the value of C1 root 2 by pi s by 1 plus a square a to the power minus k a square t. So u can be inverse Fourier transform root 2 by pi 0 to infinity u bar sin a6 dx, which means 2 by pi 0 to infinity s by 1 plus s square e to the power minus k square t sin a6 dx. So when you are going to solve the differential equation with the help of Fourier transform, it is very difficult to get the appropriate answer, but you have to reach up to the integration level. After this you can easily solve it by the numerical integration method, because it is beyond our scope to pen paper method. So till now what we have discussed is very much important for solving the differential equation with the help of Fourier transform.